I introduced white noise in a previous video, and I should have added one more thing about it. We said it's zero mean, and the autocorrelation function is just a function of the time difference, tau, not the absolute times. Therefore, white noise is wide sense stationary. Now, what if we integrate white noise? Take unity white noise as an input, this F, integrate it up to time t, and that's the output x. Let's look for all the things we normally look at for a random process: the mean square, and the autocorrelation function. Here's the relationship between output and input. Since F is unity white noise, its autocorrelation function is just the Dirac Delta function, delta of tau. The mean of the output x, take the expectation of this new function of the input, and because integration is a linear process and the limits are just constant as far as the expectation goes, it's not random, we can bring the expectation inside the integral on whatever's random inside the integral. So we're taking the expectation of white noise, which is zero. So the integral of zero is zero. So the input mean was zero, the output mean is zero. Now the mean square. Again, it's the expected value of this thing at two different times. Actually, the same time, excuse me, the same time. So we take this thing and it's just squared, so it's the product of itself with itself. But we'll use different variables of integration here, keep them distinct. And this product becomes a double integral. Again, we bring the expectation inside, taking the expected value of this product of white noises, which is the autocorrelation function of U and V, but all it matters is the difference between U and V. So its autocorrelation function is Dirac Delta function with an argument U minus V. Guess we could use V minus U, but okay, so how do we take this integral? It involves a Dirac Delta function. Well, to do that, we're going to use the sifting property of the Dirac Delta function. And what matters is when the argument of the Dirac Delta function is zero, as long as that happens inside this interval, this inner integral interval, then that integral evaluates to whatever's outside the Dirac Delta function when the argument is zero. Well, in this case, there's nothing outside, just one. And we'll get a zero when U equals V. So this box here up to T for both U, we're integrating over a region in UV space. We'll plot U along the x-axis, V along the y-axis, and this square here is the region of integration, the region of our double integral, where it's not zero. And this dashed line here is where U equals V. So if we integrate over either U first or V first, we integrate over U first, we're taking these horizontal lines. We'll encounter that exactly once for no matter what V we pick. And similarly, if we integrate over V first, same thing. We'll encounter this line exactly once no matter what U we pick. So this inner integral, no matter what order of integration we use, becomes 1. Then the outer integral of 1 just becomes T. mean square value of a Wiener process is T. They actually shouldn't have called it a Wiener process yet. Right now, it's just integrated white noise. Spoiler alert, it's a Wiener process if the white noise is also Gaussian, because a linear operation maintains Gaussianness. Okay, now the harder one, autocorrelation function. And we're going through some of this now because it's kind of going to come up later in the course using these techniques of the Dirac Delta function and the sifting problem. So this is going to go beyond just examining the Wiener process. So what does this autocorrelation mean? It means the expectation of its product. Again, now we have two different times. So these upper limits are going to be different. There's a T1 and a T2. We'll make U correspond to T1 and V correspond to T2. So this product becomes a double integral, but I have to be careful. These upper limits have to match the order of integration. So if I integrate over V first, that corresponds to T2. U corresponds to T1. You have to be consistent how I label them. So again, I could bring the expectation inside. It looks the same as before, except now I don't have the same, with the mean square, the upper limit was just T for both integrals. Now you got a T1 and a T2. So the order of integration has to match these limits. And let's look at that order of integration because we're going to have two possibilities here. If T1 is greater than T2, the region of integration, this double integral, is going to be this rectangle here. U equals V, the same dashed line. If you look at this, if I integrate over, let's see, V first, but I'm to the right of this point, I'll never encounter that line. And I don't want to have to figure out where that happens. If I integrate over U first, it's more convenient. I'll encounter this line exactly once, no matter what V I pick. So for T1 greater than T2, I want to integrate over U first. Similarly, when T1 is less than T2, I want to integrate over V first. So here's the two cases. If T1 is greater than T2, I integrate over U first. Just like before, that inner integral is 1, but now the limit on the outer integral is T2. So I get it. If T1 is less than T2, it's the same kind of thing, but now the upper limit is T1, so I get a T1. The ultimate result is that this autocorrelation function is the minimum of T1 and T2. So we just show here that the integral of white noise is not wide sense stationary, even though white noise is. This is kind of difficult for students to understand the first time through. So you might need to come, if you really need to understand this, you're probably going to have to come back to it. So here's the summary of the Wiener process. Its mean is 0, its mean square is just T. Its autocorrelation function is the minimum of the two E's in your process. If the input is simply white noise, I'll call the output Brownian motion. But if the input is Gaussian white noise, that's when the output is called the Wiener process. It is also Gaussian, not stationary. Let's see. A quick example of maybe some manipulations here. We'll say X is a combination of a Wiener process, W, in a time-scaled Wiener process, this second guy here. What's all the good stuff? Mean autocorrelation function variance of X. Well, the mean's easy enough. A linear operation here, basically, and everything's both W's, the means of the white processes and the Wiener processes. Shouldn't call it white, Wiener process. 0. So the sum is also 0. That's easy. That means variance is just the mean square value. But since we're asked to find the autocorrelation function, it's going to be easier to find the autocorrelation function first and calculate the mean square from that, rather than calculating it on its own, I think. So here's what the autocorrelation function is by definition. It's this product. And like usual, we substitute in what it is. 3 different t's. And let's multiply these guys out. And each one of these is an autocorrelation function of a Wiener process. This one's just the 2 times, just one's T1 A T2, T1 T2, AT1 and AT2. They're all the arguments. And we just saw how to evaluate those. They're the minimum of the times. If you put all that together, you get this. And from there, it's easy enough to find the variance because this is the mean square value. That means I just put in t for both of these arguments in the autocorrelation function. Simpler variance. And that, kids, ends my module on random processes. Next module will be linear systems. This is still all part of a course called Random Processes and Kalman Filtering. So next subject is linear systems.